So, yesterday we started discussing symplectic involution of K-free surfaces and of K-free type. So let me quickly recall that we just described their pixel loci, right? The last thing we saw was the following here. So, if we had S iota with SK3 and iota symplectic involution, then the pixel locus is 8 points. And that was the first part. The second was that if you have now a symplectic involution on a fourfold of K-free to type, then the pixel locus is 20 isolated points and one K-free surface, if you want to add here. That's one K-free. Okay? We discussed a little the proof apart for the last deformation argument. That's the story, right? But I'm not sure. So maybe I'll say. No, let's do it. So let's see an example. Of course, let's do an easy example. That is a good way to warm up. So let's consider the Hilbert scheme of a K-free surface. Okay, let me remember you that you can use as a resolution of the second symmetric product of your surface. Suppose now that you have an action of a symplectic involution on S. Okay, so that here you have iota times iota acting, and you do the equivariant construction. So you get factorially the second symmetric an evolution on the second symmetric product, and in fact you can show that it lifts to the resolution, the Hilbert charge. So that's what we denote a natural involution. Okay? You naturally get it induced by an involution on the K-free. So it is now to give in one, seeing that the pixel locus is this one, right? So then I want us to discuss this because I want to say what is this description. Okay? So let's see. We want to study this. We know already what we should get, but let's see why. What are fixed points over there? Of course, you can track pair of fixed points here, right? So if you have Pi, Pj, you get, let me use these brackets to say that this is an ordered couple here, with I different from j. And well, if you do 8 over 2, you get exactly 28. Okay, so these are 8 over 2, which is 28. So this gives you the isolated pixel point. So where the K-free comes from? Well, you look near, and so this will be, let's say, Pi. Let me be very precise with the notation, I know, but just to understand. Then, if you think about it, you have orbits of your involution because it's order 2, and we are in a Hilbert scheme of points, of 2 points. Okay, so if you take a pair of P and the image where the involution is fixed, okay, and that gives you a surface. In fact, you have to take the closure because you're linked into the resolution. So inside here, it's clear. Let's say that what you obtain, if you think about it as that one, it's exactly the resolution of this portion. And in case you were wondering what I should do with the pairs Pi, Pi, which are in the diagonals or in the pixel locus, well, you get all the P1 over it, which is fixed, and it falls inside. It's exactly the rational curve in the resolution over the portion. Okay? So this is what is called the Nikulin surface. it's the resolution of the quotient of our S. It has been studied. And you can actually describe completely the family, because you can say what is the lattice polarization that you have on it, that work not only of Nikulin, but also Garbagnati and Sartre. Okay? So I'm saying this because now I want to go to study Nikulin orbifolds, and we chose that name. So it was weird. They were already a lot of studied before, but no one was giving them a name. And so we decided that keep calling them type and prime was a little vague and not really easy to remember. So we thought of this construction and we decided for the name Nikulin orbifold. All right. So before we go to that, we still have to say something about symplectic involutions, because we discussed pixel loci and not yet lattice invariance. Okay? So what I want to recall now is the action on the lattice of such a symplectic involution. So let's say that this is theorem A. In parallel, let's go for the other invariance that we discussed, that's theorem B. So again, one, let's see what happens for K3 surfaces first. This is due to Nikulin. For some more reason, probably. Or fun. So let me just write like this, okay? It's always a symplectic involution. Now let me repeat anytime this. Then, sorry, now the notation is not brilliant. So this was the co-invariant lattice. That's why it's not brilliant. So let's call this sigma, so that there is less confusion. Okay. So the co-invariant lattice is isometric. So this lattice, what does that mean? So it's a negative definite lattice of rank 8. Its quadratic form is the quadratic form of E8, the negative definite, multiplied by 2. Okay? So all roots will have square minus 4, and all products will be the non-zero ones. As a consequence, we know what is the mark, that we know what is the invariant, because this is the orthogonal of the invariant lattice in a unimodal lattice. We can compute that you obtain that the invariant lattice is this one. Second part is due to Mongardi. So if you now have X iota, a symplectic involution acting on a fourfold of K3 to type, well, it's the same. Sorry, the notation is the same. The co-invariant lattice turns out to be the same. What is different is it's the invariant lattice, because now we are embedded in the lattice of K3 to type, and we gain an exceptional divisor, right? We've discussed this. So the invariant lattice, you compute it, it's the same, but so the exceptional divisor is invariant. And so it's out. So you get minus 2, 3. Okay. Let me give just a sketch of the proof. So for the first part, what you actually do is you write the isometry, which is this one. It's easy to describe. So in K3, it was, let me recall, the evolution is doing nothing else but exchanging these two properties of it. So let me write like this. This is the action. In fact, you don't know that there is a iota yet. You start from a big I, which is just an isometry. Okay? You say, let's start with the isometry, which exchanges these two copies of A. It's clearly an involution. I hope this doesn't bother you. Okay? It's an isometry over K3. Notice that this is exactly the co-invariant, because the anti-invariant part, for now let me write with the big I, is spanned. Say that here basis is E1I, and here is E2I, for I from 1 to 8, the roots. But the anti-invariant part will be the difference between the two, with the same answer. This is square minus 2, this is square minus 2. They are orthogonal, so that's why this generator has square minus 4. And if you check the product, you see that the quadratic form will be exactly this one. Okay? Then, of course, this is just an isometry, so the rest of the proof is, well, observe first of all that this doesn't contain any class of square minus 2. The minimum is squares, all squares will be multiples of 4 inside this lattice. Okay? And this tells you that you can apply Torelli for K3 surfaces. And you get a lift, which is an involution. By Torelli, you know that it will be symplectic simply that by the signature of this and of its orthogonal. We'll discuss this. Okay? Okay, there's the last part, because this is one choice. It gives a symplectic involution, but I'm claiming way more. I'm claiming that all symplectic involutions have that co-invariant lattice. So the last part is proving that this one is unique up to conjugate. With these properties, of course, involution and this signature of the co-invariant lattice. That's the first part of the proof. Okay. For the second part, let's look at our example. It's still on the blackboard, the natural one. It's a special case, of course, right? But there, you can see, as I said, that if you look at the exceptional divisor, there it's clear that it is invariant. Okay, for a natural automorphism, it's clear that the exceptional divisor is invariant. It's truly the exceptional divisor. I mean, we are on a Hilbert scheme. If the automorphism lifts, it's preserving the exceptional divisor. There is only one, it cannot do anything else. Okay? So it's clear that so the proof is in part. Check that the statement holds for the pair sigma now, sigma 2, iota 2, okay? And this is basically relying on the observation, in fact, by Bottel and Sarti, when they studied natural automorphism on Hilbert schemes, that the invariant sublattice has to be the invariant sublattice on the K3 plus the exceptional divisor for a natural automorphism. Okay? So the fact is that this is the iota embedded inside the cubic lattice plus minus. Okay? Geometrically, it comes exactly from what I said about the invariance of exceptional invariance. And that's it. That is the first part. The second part is showing that any pair x iota can be deformed to a natural result. Which, that I mean, of course, we can always deform. So saying that fourfold is of case to type, it means that in the big modular space, you find a deformation for the schema of points. Okay? That's basically a definition. But here we want to deform along the symplectic evolution. Okay? So, in fact, we want an evolution on all the deformation family that we choose. All right. So that's the end of the proof. Maybe it's a good moment to discuss a little deformation theory. At least I wanted to do way more in general, but I don't have time, so I'll do just for symplectic evolutions. So that is probably, I don't know, maybe a 5.3. I'm not sure. Yesterday we should have arrived at 5.2. If I was correct with my notes, but that almost very rarely happens, so tell me if it's different. Okay. So, modular spaces. So, first of all, fix the deformation family. ML. Let me recall you briefly, I won't recall the theory. We can construct a modular space of irreducible holomorphic symplectic manifolds of a given deformation type by choosing a marking. So we do a modular space of marked pairs such that X has a theta is an isometry between the holomorphic lattice of X and L. I can say like this because for now, known deformation families of irreducible holomorphic symplectic manifolds all have different lattices. It's not that it is proven that there is a unique deformation family for any lattice, but it's what we observe in nature. So I can say like this. All right, and let me remember that you have a period map P, which goes to the period domain. I think we can use this notation. So I'll try to adapt it with this. So these are periods, which will be nothing else as our symplectic form inside the complexified of your lattice. And then it's known that periods satisfy the following two, they are anaquadric and they pair positively with their conjugate. Okay, so what does it do? It takes theta and sends it to the class of this line. So we take the image, to be precise, the tensor C. There are too many parentheses, maybe. Okay. Inside there. We've already discussed that it's a local isomorphism. And very general points inside here are non-projective. Okay? Because in fact we know that the Rosseveri has to be hyperbolic and it's orthogonal to the period, in fact. Right? Once you choose a period, you know what is the Rosseveri of the points in the fiber of the period map. And so you know that for your fiber to contain projective hyperkählers, the period needs to be on the orthogonal to class of positive square. We need at least one class, right? Okay, So now let's get to symplectic evolution. If iota is a symplectic evolution, I'm pretty sure that we discussed so that the transcendental of X, transcendental lattice, is contained in the invariant lattice, and just because the symplectic form is invariant. Okay? As a consequence, its orthogonal contains the orthogonal. Saying that we now want to identify the subspace inside here, which contains, it will always be marked pairs, but in fact we want it somehow to be the target of a forgetful morphism where we are sure that there is a symplectic evolution. Okay? We need a lattice polarization, that's what it's saying. Sure. Let me introduce a notation which is very bad. It's just for the sake of the. I would never use it in a paper, but it's very convenient for what we are going to do. Okay, so notation just for today. Let me denote by M and P the modular space of pairs XF with X of type L, of type K3N, sorry, and with N equal 1, I mean K3, okay, and F of order what is that, P, symplectic. We use totally another notation, but it's more complicated, so let's keep it like this. That's what we want to describe inside. And so for now, it's just a subset. We want to describe it inside here. Okay, I'm not putting the marking just to be quick. You need the marking and you need compatibility with the isometry, but let's keep these technicalities here, please. Yeah, we definitely need to skip at the point, we don't get to the point. Okay. All right, so it's not too difficult to see that, as I said, you need the lattice polarization. So everything in here has to be algebraic, which means that the period has to be in its orthogonal. So inside Ti. Okay, yes.
Why do you have an inclusion of moduli spaces? Can't that be several automorphisms? Why is there an inclusion of moduli spaces? Can't there be several automorphisms?
No, as I said.
Okay.
It's a very imprecise thing. In fact, you have an inclusion with marked pairs such that the marking recovers the action of the automorphism. Okay? Which is way more technical to write.
Okay.
I was just wanting to say, I want to track the subspace of marked pairs where I know that on the hyperkähler there is such a thing. But this is not well written. Okay? It's just an intuition. Alright, so we have a restrictive. We get from N and P, if you look what the period can have been, you see that it will be in what we would denote dTi. Iota, so, which is exactly the same thing, except that in of L, I put this line. It's same signature, so there's nothing changing in the geometry. Okay? If there is a symplectic automorphism, the period has to be in the invariant. I'm not saying anything more. I'm not saying that it is subjective, I'm not saying anything, but we get a restricted, for sure the image of this will be contained, via the period map, will be contained in here. So if you prefer, you can write like this. And this is of dimensions. Okay. This comes from the fact that locally, if you want your involution to go along in the deformations, inside deformations of X, you need to consider the invariant part. And these are controlled it's an easy computation by this, the invariant part of the H1. Because you know that these are controlled by the H1 of the tangent bundle, and we have an isomorphism with omega 1 of X. Depending on symplectic or non-symplectic, views will be equivariant or not. So you have to track what you obtain once you pass to H11. For symplectic, you get the invariant part of the H1. So that's what happens locally. And from there, you deduce that this is still a local isomorphism. See? Over here, you get an involution on the family, let's say. So if you have a family here, over here you get a family with a big involution, inducing an involution on all fibers. That's the idea. Okay? You get an involution on all the complex family locally, which restricts the symplectic evolution on each fiber. Now we go back to our symplectic evolution and shall say that we can describe M12 and M22, which are the two ones we are looking at. That's again work of Nikulin and of Mongardi. It's the final part of the results we need to recall. And they say that the K-free surface carries a symplectic involution if and only if there is a copy of E8 minus 2 inside, primitively embedded in the neuron sedate. Same goes for K-free 2 type. In other words, M12, as I said, there's one I using K-free surfaces, okay? And the here M mutation. And M12 is exactly what we would call, so these are pairs sigma eta, such that eta to the minus 1 or P8 minus 2 is contained primitively inside the neuron sedate. Again, the same goes. So here it is in ML, MLK3. Same works for, let's put K3 here, and let's put K3 here. For K3 to type. So this is again Nikulin, and this is Mongardi. we have a symplectic involution on a K-free surface or on a four-point K-free type if and only if there is a primitive copy of the H minus 2 embedded inside. Okay. Let me go back 1 second to the period domain, dTi. As I said, geometrically, it's not very different, we know from classical results in geometry, since the signature is the same of L, it's free something, it's not different from the period domain that you find for the full family of formation family of irreducible holomorphic symplectic manifolds. In particular, the very general element over a point there will be non-algebraic. Okay? So, remark, very general element but that's also in general for all primes and lengths, in fact, is non-algebraic. How do we know that? Because the very general one will not have a containment here, but it will have a quality. The non-severi can become bigger by Apelsin continuity, but on special points. That's in here. Because okay, so there's no, it's not hyperbolic, you see. And now, that's before switching to the Nikulin side, let me mention that you can ask yourself the following question, and you can ask for all other cases, okay? Which I mean, with that I mean higher hands for different prime orders, for different deformation families, okay? What is the note? What is what we call the algebraic lattice losses inside M and 2. This has been answered for n equal 1 and 2. What do I mean? Let's look for algebraic elements inside here. The very general is non-algebraic. Where are the algebraic ones? So that's the question. This has been answered in 2 theorems. One for K-free surfaces by Van Gemen and Sarti. And if you think of the warm-up example of the first lecture, you will find it in this paper. Okay, so what they will prove, they show that S is a projective K-free with a symplectic involution. You need a polarization to study the neurons available. Right? You need a class of positive square. And so I can put it in terms of loci inside here, but let's write it in the easy way. If and only if the Néron-Severi of S contains one of 2 lattices, so either it contains this lambda to D, which is nothing else but a class of positive square, plus the orthogonal sum with the 8 minus 2, so D positive, or it contains an overlattice of it when it exists. So this is an overlattice. Of lambda to D. This overlattice exists if D is even. So for degrees which are multiple of 4. Okay? So all these are loci, and all these submodular spaces, these are lower dimension, okay, because we have one more class in the Néron-Severi. So they are in codimension 1 inside here. And they give you the full description of the algebraic distance. We did the same with Gregor Skapuska, sorry, I'm not writing the full names, and Alice, which goes here, Garbagnati. We proved that the analog result for K32 type, so SK32 type projective with symplectic evolution. Now, the condition on the coinvariant lattice is the same. So we want E8 minus 2 inside. We want projective, so we want a class of Bouville-Bogomolov square 2D with D positive. Okay? So that's exactly the same on under observation. We either have this inside, or we have this over lattice inside. Now, the difference is that each of these two has a unique embedded in the lattice, lattice, but this is no longer the case of in the K32 type lattice. Okay, so if and only if. So,
what do you mean by not related?
Hmm?
What do you mean by not related?
Over lattice. So this is an finite group extension.
That's it. So lambda 2D in this case is not primitive.
It's still rank 9. It contains this one, but this is not included in a primitive way. So the quotient will be a finite group, so the discriminant is changed. Okay? In fact, you are gluing a class here. You are gluing the sum of these plus one specific vector inside here over 2. It's not integral here, but it's integral here. Okay? Sorry for not recalling the technicality. Okay, so if let's say X iota belongs to one of the following families. Let me write it. Either the Rosse variables contains lambda to D, but you have up to 3 embeddings depending on D for this, yes?
Sorry, so just to clarify the statement, you're saying when D is 1 mod 2, this lambda 2D is primitive?
It exists. So this doesn't always admit an overlap. It depends on the parity of D.
Okay, right, okay.
Okay, so when it exists, it is an option.
Okay, I understand.
Okay, but it is not always possible to construct it. That gluing is possible only when this is even.
Only when, right.
Okay.
Great, yes.
It's not a matter of the fact that you can glue something. Okay.
Clearly arithmetic, yeah. Okay.
Yeah.
Okay, great.
As I said, so here again, in the Rossevere we will find this or this one it exists. The condition is the same. But now here we can have, we always have at least one embedded. That I mean up to isometries, okay? We preserve the embedded. So here we have up to 3. I won't write, I mean, I can give you a total one which are non-isometric, but I'll keep this detail now. It's just to say that there are up to 3 embeddings. You can find all the possible transcendentals. Let me just write that this is for all D in N. This you find J2 when D is covering 1 over 2. So you know that this part is not. This you have 3, so you get 3 of them when this is congruent to 3 modulo 4. It's the case of the funnel, the family of the funnel, the first one which appears. Okay? Or D is even. And whereas this, luckily, this when it exists, it's always with a unique embedding. So it always gives one family, which I call J tilde. If D is even. As I said, there is a table with all the transcendental lattices, so the orthogonals of these, which completely identify the primitive embedding that I'm discussing, but I have no time to say that. The only thing I wanted to mention is that there is plenty of geometrical constructions lacking in those families. So, thanks to Mukai models, When given entirety, well, and two explicit projective models that we have since Sandona, let's say, when given entirety can construct the general element of their projective families for all the small degrees, okay? If we look at small degrees here, we know a few constructions, what do I mean, of the projective K32 type, and also the evolution on it. I actually made part of them in my PhD thesis when I wanted to give evidence for the conjecture that there was no abelian surface, okay? So, D equal 1, you find that one of the two families is D equal 1, one of the two families is given by a symplectic involution on the EPW set, double EPW set. And it's not a surprise because you're adding a class, a polarization of degree 2. Okay? Doesn't come as a surprise. So the only observation that I wanted to say is we know models for, let's say, I should have put a D in the names. So for J1 of lambda 2, we know, and actually also for J2. But then things get worse. We know nothing for, we know J tilde for lambda 4. We use varieties, so hyperkähler coming from varieties to give this example. And we know J3 for lambda 6. If I don't remember wrong, it's J3, yes. Which comes from a construction of the family. You put a symplectic involution on a family. Okay? All the others are not known. So there's plenty of work to do to find geometrical constructions. In the sense, we can prove, of course, since we know more or less the general severity of the very general element, that they are all birational to some moduli spaces of sheaves on a given K-free surface, eventually twisted. That's a formal computation that you can do with the theory of moduli spaces of sheaves. But the problem is that K-free surface will have Picard rank 7, so it will be algebraic, so there's no way to embed E8 minus 2 inside there. What I mean, the K-free surface will not have a symplectic involution. Okay? So if you want to look for the involution, it really has to appear in dimension 4. It doesn't come from dimension 2. So there's plenty of construction to look for. Talk about the others. Okay, that's all I wanted to say for symplectic involution. In the last minutes, I go to Nikulin orbifolds. All right. So that's a 6. In fact, I'll give immediately the definition, but I think with a better title is orbifolds of Nikulin type. We said that the symplectic involution preserves the symplectic form. As a consequence, since it is invariant, it goes down to the quotient. On the regular part of the quotient, you find the symplectic form. Okay? So, while let me say that this is an example of a construction that you can do with all finite symplectic group actions, and this has actually been attempted by Fumene, and then there will be recent work appearing on the archive, I think, by Bertini, Capasso, De Bara, Grossi, Mauri, and Mazzon, computing all possible quotients that you can get via symplectic evolution, and that you can, so quotients itself, you can always get. The question is whether you can do what we will do now, so which is a Q terminalization, which turns out to be reducible to symplectic variety. Okay, and that's not always possible. Depends on the codimension of the pixel locus that you find. And it's done to compute possible Betty numbers of deformation families of singular analogs of irreducible holomorphic symplectic manifolds. Okay? So there is many work to do, but this family has been studied way more. So let now x iota be a pair in. Now I have a notation, so I can just write like this to say that it is K32 with a symplectic evolution. As I said, it's bad notation, but it's useful to go quicker. And consider the quotient. I have my S. I do the quotient. Okay. This is singular in 28 points along a K-free surface. But the type of singularities on the 28 points and not in the K-free is quite different. In fact, what Markuchevich-Tikhomirov proved, sorry, now I'm always shortening the names, otherwise we don't get to the end, is that there is rho, this is a partial frequent resolution over, and now we need a name for our fixed K3, and so let me say that here we have x iota, and I call S. Now there will be no confusion with other S, so I can use S over S. So you can resolve, since it's codimension 2, the singularities of the K3 surface. And what you obtain here is something which is pre-factorial, clearly, with 28 terminal points of type the easiest that you can find, because in fact it's a quotient by a Z mod to Z action, so that's the type of your singularity. Okay? Of course, you can always construct this the other way. Yeah? You can pass through the smooth one. You first blow up sigma, induce an evolution over here, and then make the quotient. That's always allowed for this kind of blowing up surfaces. Okay, what else should I say? So this is what is called phi is a Nikulin orbifold. I call sigma the exceptional divisor over the image of the K3 surface. Okay? That's the exceptional divisor.
So one doesn't take a full smooth resolution because that doesn't have the IHS like properties we want to preserve.
So here you see that it's exactly four.
That's why we like it. Okay.
Yeah.
Great. Sorry, I'm very I'm very naive about these.
No, but it's I was going to tell you in a second. That's very good. So this is an Nikulin form, but I wanted just to finish the definition. And so we have, let's put it immediately. Phi is what we call the irreducible symplectic orbifold. So that it is an orbifold, you can guess, it just means the locally of the charge instead of the Cn, you find the finite quotient of Cn, okay? That's very naively. But in fact, it has a symplectic form, and not only, so that means that the symplectic form spans the H to 0, as in the smooth case, and that the regular locus is independent. That's the strongest condition, I would say. It's clear that it is all simply connected. Anytime that you have a fixed the finite action with fixed point, the quotient is simply connected, but that you have for the regular part. Okay, this and projective and all projective wise, so this in general won't be projective, okay, because X is not. But when you have a projective one, are what nowadays they call irreducible symplectic varieties. Okay? which is given in the algebraic setting only, so I need to precise that I put that in one. So they are example of all definitions that you can think of as singular analogs of irreducible holomorphic symplectic manifolds. And what else I should say? Yes, these were studied long before these definitions appeared by Fujiki. So if you look for all the literature, you should look for V manifolds. V manifolds.
Oh, V. Sorry. V, okay.
So in Fujiki, they are referred to as this. Okay? Yes. All right. Okay. So the good thing is that Mene did quite a big work on these irreducible symplectic orbifolds. And thanks to work of Mene and Namikawa before. Hope I'm not forgetting someone, otherwise I apologize. We have a quadratic form on BH2, exactly as in the book case. We have the Torelli theorem, global Torelli theorem, and we have the Carlton, the wall and chamber decomposition. In fact, by Campana, these are building blocks of orbifold, irreducible orbifolds with trivial circumference. So we can do our theory as it is, but we need to compute first of all these two, and that is done by Mene. So let me record the result. But first, let's give the last definition. An orbifold of the Nikulin type is a deformation of a Nikulin orbifold. Not everything in this family will be a partial resolution of a quotient. We'll see it in a second. That's basically due, as for the case of Hilbert schemes inside the family of K-Friedel type, to the partial resolution. We are introducing an exceptional divisor, but that means that the B2, the second Bethe number, will grow up by 1. And that is controlling the number of deformations that we have. So we will have orbifolds of the Nikulin type, which are not partial resolution of quotients. Okay, there is more in this family. Okay, now let me recall just the results by grade 1 that I wanted to look at. Just to be sure not to say something serious. Yeah. Not Mene. So, for a Nikulin orbifold, Y, this lattice is isometric. So, the invariant part, Pi, of its symplectic involution was of rank, so it was 3 copies of U plus 1 copy of E. So it was rank 14. Okay? And it was 15 on K32 type, because we had also the -2 plus the exceptional divisor. So that part goes down. The quadratic form can change, but the rank will stay. Those are the generators. Okay? Plus the exceptional divisor. So over Q, the generators will be the push down of the invariant, the generators of the invariant lattice, plus the exceptional divisor that I introduced. And he computes over Z what is the form, that's the difficult part. So that is, sorry, 3 copies of the hyperbolic plane. Again, the form is multiplied by 2, so here the form is 0, 0, 2, plus E8 minus 1, plus 2 copies of -2. So that's, in particular, B2 of Y is 16. Apparently, from the work I was mentioning before by Mirko, Annalisa, and others, it's the maximum Bethe number that they can achieve before getting to smooth ones with 22. Okay, so apparently there is a gap between 16 and 22 for now. Not that there is a reason for that. So what else should I say? Well, yes. If you want to look for the class of exceptional divisor, for delta 1, delta 2, there's two classes of square minus 2. Sigma is the difference of these two generators, and in particular, Cy sigma is minus 4. Okay? Good. So corollary of this theorem is that if we are really on a Nikulin orbital, so on the resolution of the quotient, and the Veron severity of X is the very general one, so we are the non-projective one, well, the only class that you can find below is the exceptional divisor. So we have a published work which depends with the cluster computation of Meneris of the monodromy group, which is not finished yet. Finita. So let's say work in progress. Y is an Nikulin orbifold if and only if the Y contains a class of square minus 4, which is the other direction, okay? And that would imply that the resolutions of partial resolution of quotients are dense in the modular space, with more or less the same proof that we have for Hilbert field inside the modular space of 4 But yeah, we need to check first that, so the thing that is missing is whether there is a unique orbit of classes of that type, of square minus 4 or not, with respect to the action of the monodromy group. I still use 2 or up to 5 minutes to finish.
You started late. This is fine, yeah.
Ah, okay.
Yes. You still have 5 minutes, certainly.
Okay, good. Let's see if 1 is enough. I'm not entirely sure, but let's see. Okay, so these are orbitals of Nikulin type. There's plenty of questions that you can ask yourself now. As I said, you know everything. I should remark that Meneris computed even numerical classes of wall divisors. And let's say most, I think Erguat told me now he has a proof that it's the full monodromy group, but I didn't see it, so let's see. Let's say most of the monodromy group. I think it's all. Okay? So we really know, even numerically, everything as for K3 to type. So you can really attack many problems on this class. What I want to finish with is, okay, just mention very quickly that from this theorem, we computed, by using Gregoire computations of intersection theory, what are the families of projective resolutions of quotients. And we get all of them. Okay? They are all with pickup rank 2. Because they are projective and there is the exceptional divisor. So we have a full picture of which things you find in codimension 2. Okay? And for one case, we could produce a locally complete family, degenerating one of these families of resolutions. We could deform it to the very general one and find a locally complete family of orbitals of Nikulin type of degree 2. There are two possibilities for a polarization of degree 2 for orbitals of Nikulin type. You can have divisibility 1 or 2. We found the one with divisibility 1. So, and we have more or less like O-graded DPW6, they are constructed as a certain double cover. Okay? I won't speak about that. I think that a good way to finish is the following conjecture. So, which is open over the integers. So let x iota and m to 2 and sigma. No, I call it that, I think. The fixed K-free surface. Then the transcendental lattice of the Nikulin orbifold associated to the pair, okay, I'm not saying y constructed starting from x iota, is isometric over z to the transcendental lattice of S. In fact, we expect it to be Hodge isometry, but the Hodge part is clear. Okay, let me say two things to finish. We proved, so what we proved is the conjecture holds over Q. So conjecture holds over Q as is not only as a isomorphism of all structures of weight 2, but it's a rational isomorphism. And it's true in all the cases we could test. Also, it holds over Z for all pairs of natural isomorphisms. But these are for dimension 1 side. Because you're taking Picard rank 8 for the K-free surface already, so the Hilbert scheme becomes Picard rank 9, so it's codimension 1. Still, here it's easy to compute, that's why I gave the example. Nikulin surface are characterized. We know what is the non-severe group by work of Nikulin, Galvagnati, and Sarti, and we could compute that the lattice for the Y is the same. Okay? It holds also for some of the projective embeddings I mentioned there. In particular, I think we tested it for J2 and probably J3. So J2 for lambda. I think we tested for this. If I'm not wrong, anyway, please check on the paper for the correct one, numerology. But it should be, I think we could check it for the fun example from the exact one. But then it's more difficult because there you need to compute the Nerone-Severio of the fixed K-free surface. That's the part which is difficult. You get control of the transcendental lattice of Y quite well. Instead, we don't have a standard way of computing Nerone-Severio of fixed K-free surfaces. It's not something you deduce from the environment, so from the K-free to type 4 in which it sits. Right? So you have to compute looking at the geometry, and sometimes it's doable, sometimes it's a difficult question. Okay, so there's some work to do here, like proving or disproving the conjecture over the integers. Because, of course, somehow I think that you need to find a case where vis-a-vis Fourier-Mukai partners if you want to find a counterexample. Okay? But, yeah, that's all I wanted to say. Okay.